ti introduco, dai. Okay, we can restart. There are some organizational words by Professor Santilli.
Thank you, Professor Corda. First, please be punctual. We start now a very heavy schedule of very exciting things. Try to be as punctual as possible. A few announcements and a few suggestions. Our foundation has a few copies left of the translation of the original lead thesis by Professor Trell. If you want one, they are complimentary. Just send a message to Richard Anderson at the foundation. Say, Richard, send me a copy, a complimentary copy of the literature. You have to give complete address, otherwise it will not. Item number 2, for tomorrow, for the formal reception by the Eccellentissimi Capitani at the government, they want also tie. Not only they want a jacket, they want a tie. And the ladies must have either to be very elegantly dressed or to have a jacket. There's very little I can do. And yes. Okay.
If you don't have a jacket, after the end of the afternoon section, I can accompany you to buy it in a special shop.
Yeah, tonight, Professor Corda can help you to buy ties at the department store, which is downstairs, but you can go by bus. Now, regarding the workshop, these are essentially the rules. Rules number 1, very strict. In respect to the speaker, we don't. Please, no question is allowed during the presentation. Absolutely, it's a very, very rigid rule, because in the past we had political interruptions to prevent the rest of the presentation. So we have been educated. So now, number 2, every speaker has to finish. This is a workshop, so it's crucial that we communicate. It's crucial that we express each other. And so we have to keep it the time. At 30 minutes, we have to stop at 25, so we have 5 minutes discussion. 1 hour talk, you have to stop at 50, so we have 10 minutes discussion. There will be a certain flexibility. If there are very important, for instance, today we went over time because it was so important, so there will be exception depending on the case. During the discussion also, please allow the other person to express entirely his view before interruption. Basically, in other words, we are here in the land of what I call the dignity of independence and democracy. So we intend to respect each other. We'll have different views. It's part of the scientific process. And I think that's it. Did I forget something, Christian?
Yes, there is some small changes in the programs. The lecture by Professor Diminkov, which is scheduled on Friday morning, yes, is rescheduled on Wednesday afternoon. While the lectures by Professor De Souza and Professor Moscaliur are rescheduled for Friday morning. This is needed because Professor Diminkov has to left us before Friday. Okay. And also, my lecture is rescheduled for like the last lecture of Wednesday afternoon. It was originally scheduled for Friday afternoon, but we have Professor Mosquera Kesta. We cannot come. Then he asked me to substitute him on Wednesday. Okay, we can proceed now. There is the lecture of Professor Günther Nimtz. Okay, we can hear. The first scientific lecture of the afternoon, Professor Günther Nimtz from Germany.
First, I would like to thank Professor Santilli and the Foundation heartily for the invitation to this interesting workshop. And I'm going to talk about superluminal tunneling confronts special relativity. First, I give a brief prologue because there is much to do about superluminal tunneling worldwide the last 20 years. Yes, thank you very much for And I give a brief introduction to what means tunneling, what means evanescent modes. Then I introduce some experiments, and we shall see that the time inside a barrier is 0 time, and the scattering, the time which is measured in all the experiments, by the way, in different experiments take place at the entrance of the barrier. And what even electrical engineers knew for more than 50 years, such a tunneling particle is a virtual particle. You cannot measure it except you destroy it, or you add, would be said in quantum mechanics, so much energy that you have the total energy again positive. Then I give an introduction to superluminal, or what means faster than light tunneling velocity, some examples. And if we have a superluminal velocity, then most of the special relativists will tell you that you have invented a time machine. Is that possible? Summing up, or you say, concludo. The prologue, I said there's much ado about 0 tunneling time inside a barrier and causal faster than the velocity of light. However, McColl, Hartmann, Franz, Recami, Caniglia, and Mandel, Ali, Collins, and Barker, Lowe and Mende, Esposito, Kapuscik, Xantelli, all these colleagues have calculated and shown that in fact superluminal velocity is possible, and that the space in a barrier or in a tunnel is 0 time. However, there are many physicists explaining vehemently that superluminal signal velocity is impossible and 0 time tunneling the same. For instance, if you read the books of Sechsel, Urbanke, and Feingold, recently published, they mention even our work. However, they say that's a wrong interpretation. The experiments are correct. However, the interpretation, that was not a signal, what they have measured. Now I'm here to clarify the problem, hopefully, in this lecture now. I remember first some wave optics and wave mechanics. The Helmholtz equation is usually used in the case of electromagnetic waves or of elastic waves. Here we see the refractive, that's the second derivative of a field, and this is the refractive index squared, that's the angular frequency, this is the velocity of light squared. And if the refractive index is imaginary or the square negative, then we have a wave number and a refractive index which is imaginary. And in classical optics, we said we have now an evanescent mode. The Schrodinger equation is given here, and here we have the same problem. If the energy is smaller than the potential U, then we have again an imaginary wave number, and in this case you know from the textbooks on quantum mechanics, then we speak of tunneling, and corresponding is the refractive index and the energy relation. E is the total, the energy of the wave packet, and U is the potential. So you see the Schrodinger equation is not Lorentz invariant, and from the mathematical point of view, the Helmholtz equation should also not be Lorentz invariant. And I was confirmed by a theoretician recently that this is really true, because many colleagues said, oh, the Helmholtz equation belongs to the Maxwell equations, and therefore it should be Lorentz invariant. However, Helmholtz, by the way, did not derive this for electromagnetic waves. He was studying elastic properties at that time. So from the mathematical point of view, both equations are not Lorentz invariant. There's another relationship we have used in order to interpret experiments. That's famous Wigner phase time. He developed this with Budweiser, with his PhD student in the 30s, I think, and in order to get from the scattering, from the phase shift at a scattering process some time. And if this again is 0, or then we would have a velocity which is infinite. What means tunneling? Here we see a sketch of the potential valley of an alpha decay of a nucleus, and it was explained by Gamow, Gurney, Condon and others already in 1928. Due to the radioactivity, this effect was found that an alpha particle having an energy which is much smaller than the potential barrier, you will find it, the nucleus will decay, and this is called a tunneling effect, the tunneling process, and the tunneling plays nowadays an important role. It's said that Big Bang is caused by a tunneling process, and our sun, our power station, the sun, for instance, is also controlled by the tunneling. Otherwise, it would explode or nothing would happen if there would not be the tunneling process on the sun. The temperature is too low for regular fusion. However, it is interesting, at the same time, or even some time earlier, chemists have observed a similar problem, the so-called molecule inversion. Here is an example of ammonia, and Hund was presumably the first one who said there is some probability that the nitrogen may tunnel from this side to this side and vice versa. And here we see the potential of the ammonia, and here we have one stable and here the other stable state. However, there is an oscillation from one structure to the other one, sorry, at a frequency of 23.7 gigahertz. So that means at the same time the tunneling was also observed and explained in chemistry. Now I come to wave optics. Tunneling in wave optics. We all know this Snell's law. If we have reflection at a material between, let's say, N1, the refractive index is larger than the second one, and then we have an angle which is beta, which is larger than in the thick medium. However, all these people, by the way, have studied this. Particularly Newton cared for this, what I come now for total reflection. And by the way, Bose is not Bose from the Bose-Einstein condensation. He is another famous Indian physicist who studied also optics and the theoretician, and only in 1946 and 47 Gauss and Tainchen has shown that there is a shift in the reflected beam compared to the incident. And this was, by the way, already 300 years ago by Newton speculated such a shift. Now what happens if we have total reflection? That means if the angle becomes 90 degrees, then we talk of total reflection, and there is still a wave number, but an imaginary one, a virtual one. And this was only in the 17th from the quantum electro QED investigated by Carnelia and Mandel, for instance, by Ali and by us. And we have shown that the evanescent mode is a virtual particle which is well described by the quantum electrodynamics. Now, if we place a second material to this, then we see approaching that eventually more and more of the incident beam is transmitted. And this is called frustrated total internal reflection. I was asked recently by a theoretician, why frustrated? Yes, the reflection is smaller than the incident. That's the frustration. And we have in between the two media and one a gap and a virtual particle characterized by the imaginary wave number K2. Yeah. By the way, the engineers using this in communications for many, many years, the glass fiber. We communicate from Europe to United States, for instance, for more than 10 years with the glass fiber optics. And this is also based on the total reflection, as you see here. The infrared radiation in the glass fiber is less than 100 micrometer thick. We use 1.5 micrometer wavelengths because there is a minimum of the absorption, of the attenuation. And you can use the frustration, and this is used really in order to couple part of the original signal into a second fiber. Tunneling coupler by frustration. That's what you can buy and what is manufactured. And it's funny, the valley is due to the glass and the wall is given by air, or at least by a material which has a lower refractive index than the glass. It is very difficult to measure the tunneling time with electrons, for instance, or with other particles, because the time is very short, and therefore in the 19th experiments were carried out, analog experiments. We have seen the Helmholtz equations is from the mathematical point of view the same as the Schrodinger Equation. And the experiments which I introduce now are carried out by 3 types of potential barriers. The first one is the undersized waveguide. If part of the waveguide, that's a metal plate with a rectangular cross-section, if the smallest size is smaller than the wavelength, half the wavelength, then you don't have a wave solution for this part of the waveguide, of this microwave waveguide. Then you have an imaginary solution, an evanescent mode, and then you can, the engineers are using it as a filter, for instance, so you can use it as a tunnel, as a barrier. Another barrier is given by a lattice structure, a dielectric structure, for instance, quarter wavelengths of different periodic, of different refractive index. And this is also called a photonic mirror. And such a design has a forbidden band gap, which is always the case when you have destructive interference from the reflection from the different lattice planes. Then you have a so-called forbidden band gap, very similar to this band gap in a semiconductor. And by the way, in laser technology, this is highly used because the lattice mirror is much better than a metal. You can obtain here reflections up to 99%. That's impossible in this frequency range where it is of interest with a metal due to the free carrier absorption on the surface. So in the particularly in high power laser applications, they use this type of barrier in order to have a reflector, also in the light emitting diodes and light emitting transistors. And now I come to the historical double prisms. This is an interesting design for measuring the time in the barrier. If you have a symmetric device, a symmetric construction, as I have shown here, then you only have to measure the reflected and the transmitted, and then you see the difference of the time of the two signals, of the transmitted and of the reflected, and this should be the tunneling time. If you ever read Sommerfeld's optics, then you will see he's telling us that this is exactly the analog of the one-dimensional quantum tunneling, the barrier, the red one. And now, this is one of my former PhD students who have carried out such an experiment. And you see that you can carry out this type of experiment on a huge, large scale. 40 centimeter, here we have the gap. This is perspex or plexiglass. And she carried out the experiment at a frequency of 10 gigahertz and 3 centimeter. And the result is comparatively easy, not at that time, but nowadays very simple to measure such distances and such propagation times, if there is one. And what she found is that reflection and transmission takes place at the same time. That means the time spent inside where it is an imaginary virtual particle does not need time, it's non-local. Another experiment, which is carried out, by the way, by a young professor, Caro, he said, oh, I want to have a very long barrier, 21 meter long. He's just published it. You had a cylinder, a helical tunnel, 21 meter long. Here's the input. And what he measured was a velocity of more than 500 times the velocity of C on this distance. Exactly the same frequency of 10 gigahertz. That means 3 centimeter wavelengths. That means you can carry out this type of tunneling experiments on a macroscopic scale compared to the electronic experiments. Even in the case of a tunneling diode, it was not measured until now. The tunneling time, and it would be very important because it is the limit of the time response of such a device, which is used since 1962. We have carried out also another experiment which reproduced the data. We have measured the reflection here and the transmission of a photonic barrier and found out that the reflection time and the transmission time is exactly the same. And this means that at the entrance of the barrier there is spent a scattering time, an interaction time. I will show you the time, the data. And at that, in this time, in this short time, by the way, one oscillation time of the wave packet, the signal, the wave packet learns how long and how high the barrier is. And then it decides how much I have to reflect and how much is transmitted. The time is raised at the barrier front. This is irritating in the textbooks. Usually you think the wave function and the second power of the wave function, the probability to find it, this is a non-elastic process. This is irritating because here the wave knows already whether if it's so long the barrier, then it's this way, only this puts. There is no attenuation inside the barrier. This is something irritating. It's correct. The wave function, if you would measure it here at this place, then you have this magnitude and so on. However, most of the students think, aha, there is an attenuation. This is a non-elastic process. That's not true. I think this nice picture is much more informative because here the wave packets know exactly at the barrier front how many are transmitted, and they don't spend time inside the barrier. I think it's fantastic that you measure here the height of your barrier and the length of your barrier and decide within one oscillation. And if you don't believe, I have collected from several laboratories the data of this scattering time. And what we figured out is that the interaction time at the front is approximately, depending on the lattice on the barrier, 1 over the frequency of the wave packet. And here you see that in the case of frustrated total reflection, that's what we have measured, and that's what corresponds to the reciprocal time. These are data from other groups. And we found also electron field emission tunneling time. Femtoseconds. In the microwave range, we are in picoseconds. Electron ionization tunneling, that's the recent, latest experiment was measured in Zurich 2 years ago, and they said attosecond, by the way, 10 minus 18. They said presumably the tunneling time was 0. The last sentence in their paper in Science. Here I present also elastic particles, phonons. That means elastic fields. And you see the agreement is again in excellent approximation. I found data in the microsecond and in the millisecond data. So that's tunneling in in different fields, electrons, photons, phonons. And by the way, when I talked about this at a workshop in Napoli, you say in Italy, Napoli, Naples, Neapel, Esposito, a theoretician, came to the same conclusion. So we published at the same time, in the same year, the experimental data, and he published in Physical Review his calculations, quantum mechanical and classical. And what I pointed out, this is a universal relation. However, there are now about 15 orders of magnitude in the time scale data available. So the picture of a tunneling photon is shown here in the Feynman style. This would be a polariton. It's not a pure photon in your plexiglass. You have an interaction, otherwise you would not have a lower velocity. The smaller velocity, due to the refractive index, characterized by the refractive index, that means you have a coupled photon with molecules of your medium. That's a real polariton. And then we have the gap with a virtual photon. No time, that's the time lost. And then we have back a real polariton. Now I make a short break before I come to the superluminal. Tunnel is a zero time space. By the way, there are several calculations carried out before we have measured it already. There is a universal tunneling time, the scattering time at the barrier front. Reflection time, that means reflection time and transmission times are equal. Tunneling wave packets are virtual, you cannot measure it, except you bring it back into the original material, or you add energy so that the total energy is again positive. These are theoretical data. The black, the fat, which stated this behavior, and the others are experimental values, which are in agreement with this interpretation. Now I come to this provocative, much ado about superluminal. What is a signal? I was surprised about the idea what is a signal. This is a signal, a digitized signal of your analog signal when we are phoning, or I don't know whether there is a transformer from analog to digital to this speaker. However, on the glass fiber to the United States, for instance, we send, and even in our laboratory we have a glass fiber, we send always digital signals. That means like Morse, and the half width of this is the information, is the signal. Here we have 1, 1, 0, 0, 1, 0, 1. That's the time, by the way. And this is an exact digital signal what we are using for our present day communication. And such a signal was carried out in Italy, also on the glass fiber. At that time, Longhi was working in an American company in Italy, and he had access to such digital signals, and he sent such signals through a barrier. 2, 1 is, that's the time, by the way, sorry, the intensity of such a digital signal, and this, you see, this is faster than the vacuum signal, and this is the signal which was sent through the glass, but not tunneled. And the most interesting result in this presentation, in this figure, is the frequency spectrum. Here we see the intensity. This is the window, the forbidden gap. He used a lattice structure in his glass fiber, as I have shown you. And this is a spectrum analysis of this pulse 2. That means the frequency of a 1.5 micrometer wave corresponds to 2 times 10 to the 14th hertz, and this is a gigahertz is 1 to the 9th. That means the signal, the frequency band of all the signals, of all the physical signals, are rather small. For instance, using your mobile phone, you have a, a signal to carrier ratio of 10⁻⁴. The new one, the smart one, has 10⁻³ in order to get more information. So that means he measured, and this is, by the way, according to my understanding, a signal. It's the same signals by which we communicate, as I have shown you before. And interesting is that this signal has no deformation because due to this narrow bandwidth, frequency bandwidth, you don't have any components attenuated more or less than the others. So you have no dispersion problems in this lattice. By the way, a joke, when we have published the first data, then Lander de mortuis nihil nisi bene, but he published at that time, you can make superluminal, anything superluminal, but no information. And then we sent, Eichmann sent a symphony by Mozart in the lab of Hewlett-Packard, and he transmitted it at a signal velocity also of about 5 times the signal, because we said, obviously, for an American colleague, a symphony of Mozart has no information. There is a serious problem why the theoreticians, most of the theoreticians, are annoyed about this. You see, in the book of Briand and Sommerfeld, he studied this signal, a sharp beginning and a sharp ending, And then you have to have an infinite frequency bandwidth. If you have, as I show here, a bandwidth of only 0.5 to 5 gigahertz, then your signal becomes non-causal according to Fourier transformation. That means before you switch on, you have already a signal. This is well known again from engineers in communication technique, and they have developed in every network analyzer, for instance, 40, 50 years ago, very famous mathematicians to organize functions, to prepare functions to get rid of the causal, non-causal components by more than 50 decibel in order to carry out the very comfortable Fourier transformation from time to frequency domain and vice versa. So 50, 60 decibel smaller are the non-causal by these non-physical but mathematical functions. The most famous one is called Kaiser-Bessel function, and it's nowadays used in all the network analyzers you can buy by the companies. So that's one of the reasons why it's very comfortable to use Gauss function with infinite bandwidth. Then you have no problems with non-causal. All these calculations which were carried out to show that you cannot have superluminal signals were carried out with non-limited frequency band limited signals. On the other hand, if you have such a signal, you should know since 1900 that all the frequency components, if they are here, you have an energy h times the frequency. That means such a signal has an infinite energy according to the Planck's Wirkungsquantum. So this is the problem. It's very comfortable to calculate with frequency band unlimited signals. However, your language, your speech, everything is limited. I don't know any physical signal which is not frequency band limited. And otherwise, as I mentioned before, it should have an infinite energy if you believe in the Planck's analysis. So the next comment by the theoreticians on special relativity is telling you that if you have a superluminal signal velocity, then you have a time machine. And that's not bad. For instance, if a system A, an inertial system A, sends at the time 0 a signal at a velocity 4 times the velocity of light to a friend who is riding relative with a velocity of 0 times 75 centimeters c, the velocity of light. And he also has a gun to send it back at the superluminal velocity 2 times c, then you will come back in the past. And this is often mentioned that A went to the counter of the lottery numbers was closed, and then he got this back before it closed, and then he will win the lottery. However, this is really naive. By the way, here I have given the formula for this time shift in this case. The problem is, and I have several times told you, a wave packet, even an electron or a single photon, is given a wave packet by frequency bandwidth, time, duration. And in this example, what I have given now, this was 0. That means you should have an infinite frequency bandwidth. If you have, however, as I have indicated here, a time duration, delta t, then it will come back in the future because the duration I had used here for seconds, I think 4 seconds for the 4 seconds time duration, and the distance between the two systems A and B were 2 million kilometers. So the problem is that in real physical systems you always end up in the future due to dispersion effects and due to this relation. By the way, this is used by Shannon more than 50 years ago. All the informatics theoreticians are using the Shannon equations, which are based on this relationship, that an information is proportional to the content of frequency bandwidth and time duration. So that means what I have shown you before. This is not a signal. This is no information. This is just t delta t0. So that conclusion, calculated and measured properties in all these experiments are, this was first observed by Caniglia and Mandel and by Ali, that this energy relation does not hold, does not agree with the special relativity. You have an imaginary wave number or pulse. Tunneling is non-local, as we have seen by experiments, by various experiments. The barrier is crossed instantaneously in 0 time. Tunneling particles are virtual. You cannot measure them without destroying them. We have found a universal tunneling time now for phonons, photons, and electrons, and I think it's valid for all fields. And at the end, I told you why the superluminal velocity. No, that's first once more the front and the space inside the tunnel, and superluminal faster than light signal velocity are possible, as I have shown you, and as we saw with the digital signals on the glass fiber. And when my colleague said, oh, a single photon or a single electron is not an information, or even this is not true. If I measure the radioactive decay of an electron, then I know this atom, or of a gamma or beta or the alpha particle, then I know this is no state of the nucleus. Is that not a signal? And it came out as, according to the new data from Zurich, in 0 time. Yeah, that's what I have shown you in the last 2 pictures. And these strange properties, I'm told, confront, according to the textbooks, the relativistic Einstein causality. However, according to my information, Professor Santilli is also my opinion, and we have shown the primitive causality is not violated. Always effect and cause have the proper follow. But you can have even infinite or nearly infinite velocities, much higher than the velocity of light in vacuum. Then you don't destroy due to this relation delta nu times delta t, the duration length and the frequency bandwidth. You always end up in the future. Tunneling occurs a spooky phenomenon. Thank you for listening.
Thank you, Professor. This is very fascinating indeed. Well, tomorrow we will, most of my personal presentation will be devoted to Professor Nimtz, historical surpassing of the speed of light. But please, any question? Please.
Thank you for this excellent talk. Now, when I give my talk, I'm going to basically give a physical interpretation of time as basically being an energy dispersive thing, entropic. So your zero time for tunneling, to me anyway, means there's no energy dispersed by the particle in the potential well, which basically also means it's the phenomenon is a superconducting phenomena where a virtual particle or Cooper pair is formed. So is tunneling really a superconductivity phenomena, and that's why you're seeing zero time or zero energy dispersion, the way I interpret it.
So you mean
basically when a particle
sorry.
When a particle hits the potential well, instead of a virtual particle going through the tunnel, is actually a Cooper pair, a pair of superconducting particle, which by definition is superconducting. It has no resistivity, there's no energy loss, etc. And it's this virtual particle that drifts through the tunnel at basically infinite speed with no loss of anything. And that's really, so it's really a pair of superconducting particles that's drifting through this barrier and not single. So basically the tunneling effect is what I'm saying is really a superconducting effect.
Sorry, I don't understand your comment. What you want to say? You say you don't think there is an energy you say there is no energy transport, or what?
Yeah, well, I'm just saying that tunneling is to me, the interpretation tunneling is a superconducting effect. A superconducting, as you know, a superconducting magnet. Superconductivity is basically, like example, a superconducting magnet. Electrical current can move through electrical wire with no electrical loss. That's just definitely a superconducting magnet. Basically, a pair of electrons forms a Cooper pair, and this Cooper pair drifts through this electrical wire without any loss of energy. Therefore, that's the interpretation of superconductivity. And so to me, it's very akin to your description of the tunneling effect, like a superconducting effect. So instead of this particle or this virtual particle moving through this potential as one virtual particle, in effect is moving through this tunnel as two virtual Cooper pair, which is what Well, that's what I'm asking. If it's a superconducting effect, by traditional superconducting theory says that a Cooper pair is needed for superconductivity. That's what I'm saying, is that if this is a superconducting effect, which is the way I'm sort of interpreting it or trying to interpret it, then by definition it needs a Cooper pair to drift through.
In a Cooper pair, you don't have an exchange. You have
well, obviously Ruggiero, and I'm going to get is particle and anti-particle. There's a particle moving forward and a particle moving from the past. And
that's your picker.
So that's my opinion, is that there is a Cooper pair is where I'm trying to lead this to, because obviously this is about antimatter. So I'm trying to interpret a particle going into the future and a particle going back, which forms the Cooper pair. That's where I'm trying to lead to.
That's a stationary state. The two electrons in a Cooper pair are bound by a bouncing photon. I agree. However, here in this experiment, we have, in the tunneling case, the carrier, you measure the alpha particle, you measure the electron, you measure the photon outside the barrier. And inside the barrier, it's zero time.
Yeah, in my
You cannot
geometry,
measure it.
why a particle has
Doesn't
a
exist.
Yeah.
Sorry.
If I may interpret the different view, this tunneling is the Professor Nimtz. You have exposed the very tip of an enormous iceberg that we yet to be discovered. There are many, many different interpretations that are at this time called surface. For instance, one interpretation I will see tomorrow, tunneling through a barrier is tunneling through through energy, and that is that is an interior dynamical problem. So that could be a longitudinal transition at a very high speed, not necessarily with infinite speed or at zero time. There are many things that can be discussed, but we will discuss tomorrow after we do the axiomatic part of the.
This would mean that you don't expect the Wigner phase time.
Well,
because the Wigner phase time is zero.
Yeah, the fundamental issue, which we will review in part tomorrow, the fundamental issue is the following: what are the interactions, if any, that occur in the tunneling? For instance, the 20-meter long tube and so on. There are two possibilities. All the interactions are conventional, potential. In this case, you have a strictly special relativistic setting. However, there are other interactions that are not necessarily, are suspected, not necessarily to be derived from a potential. You mentioned the word non-local. You exit from special relativity. In this case, the only way that I know to achieve an invariant, axiomatically consistent invariant, is to lift the entire formalism via a non-unitary transform. Once you lift a non-unitary transform, you see a dramatically different scenario, and it comes out of the interpretation of your beautiful work. In other words, my suspicion, again, it's a suspicion, Professor Nimtz, is a suspicion that there is so much yet to be discovered, all very interesting, and we'll discuss tomorrow, perhaps after my...
However, we have published data where we have had not a purely elastic process, where we had some absorbing material inside the barrier, and then the effect disappears gradually. If you have a guide or a lattice or whatever, if you add some interacting material in your waveguide or in your glass fiber, absorbing, then you don't have an elastic process, and then you have time. That's time consuming.
That is correct what you say. Still,
really time consuming. We have published this. We can send you the paper.
Still, other interpretations are not excluded. This is my point.
Yeah.
Should be investigated all, because this is very. We can learn a lot on. Please.
Just I wish to remark, maybe the relationship between tunneling and your idea of superconductivity can be clarified if you look at the speed. To my knowledge, the Cooper pair or a superconducting current is not propagating with very high speed. The charge carriers in metal is very low in general, so there maybe is a limit of this parallel. But this is connected to my own question. If you have tunneling over different distances, even 20 meters, then you can confirm the idea that all the time is spent at the barrier by varying the length. And then this has perhaps been done, but you have spoken in every experiment about one single length. This has surprised me, because your word vary is the length of tunneling to confirm your conclusion.
Sorry. This was carried out by us and by other groups. If you change the length, the time is still the same. That's called the Hartmann effect. 1962, he has calculated. And we have measured it first, and then some other groups have measured it and reproduced it with laser pulses and so on. With increasing lengths, the time is the same. However, and this is a trick in this 500C, the velocity is not directly measured. You measure the length and you measure the time, and then you have this high velocity.
Yes, please. Yes. See many hands. Then who was the first? I don't know.
I just wanted to say that in the case of superconductivity, we have a sort of bosonization of fermions. But here I think it's more general, because you should signal with phonons or electrons or bosons like photon. I think it's a deeper thing.
Even phonons, lattice, simple lattice oscillations.
But let me
Sorry.
perhaps I can clarify, Professor Levin Ying. He's not referring to a conventional Cooper pair. No. It's a completely different. It's because he assumes the existence of a mirror world in which every particle there is a conjugate. So his viewpoint is while there is a propagation, there is on our world there is an anti, which he will define in his. So the word superconductivity is maybe a little bit misleading, but however the comment is very deep and it's part of the many interpretations that are open to discussion. Please next.
I need a clarification. Which is the operative definition of primitive causality?
Only that effect comes after the cause. That's all. After the cause.
Okay.
Effect follows the cause. That's primitive. But in the Einstein causality, you say nothing is faster than the velocity of light.
Yes, this is the main objection that I have heard, around Professor Nimtz' work, which I do not accept, incidentally. Namely, that if you look at Poincaré symmetry and use all sorts of special relativity, basically you border into a space-like type of situation, and therefore you violate causality. It's very easy to prove that what he stated, Professor Nimtz, namely that you have the effect will precede the cause. However, this is the central point. However, is that those objections are based on the assumption, because it's an assumption, that special relativity is exactly valid for the condition of Professor Nimtz. I personally respect his point of view, but disagree, because there are very deep departure from the setting of special relativity, most of them yet to be understood. Once you depart, you admit that indeed there is a world beyond the special relativity, especially in those special guides. It's not in empty space. In other words, I'm deeply convinced special relativity is absolutely valid in empty space. Here we're not talking empty space. We're talking about a world dramatically different. So to be scientists, we have to admit the possibility that we are beyond special relativity. Once you do that step, then the proof of causality, you will see tomorrow, is absolutely, but it's a crucial point, Christian. Thank you for raising the issue.
Two short questions, one general questions and second technical one. General questions. It's known that classical electrodynamics establishes a limit of applicability by quantum scale domain. At the same time, in your experiments, you deal with macro scale domain. Does it mean that you establish your own limit of applicability of Maxwell equations?
Because they are not applicable to your experiments, obviously.
Would you interpret his question?
Yes, we go back to my preceding issue. If you assume, there's an assumption, the basic assumption. If you assume that indeed all the, I call it interaction, effects, call it in any way you want, everything is standard, 20th century, then Maxwell must apply. However, the moment you have something that is structurally different, and that's what we suspect in the barrier, then Maxwell equation not necessarily apply. And sorry if I complete the point. In the Maxwell equation, in this case, in this case, normally Maxwell equation have no longitudinal solution unless very fancy. But if you lift the horizon, then you'll see a covering of Maxwell equation which does admit longitudinal solution. And that could be one of many interpretations of his Standard effect with very high speed. Not necessarily with infinite speed, but it could be very high speed.
I think I understood your problem, or not your question, not your problem. The same is, I was frequently asked, you have problems with, or what is the energy propagation equation, the famous energy propagation pointing vector, yes. You cannot use a pointing vector in the case of reflection. We have shown. Nobody does believe. But I can say you a very simple example. An electrical engineer has an open end on his wire, and so he's losing some energy. And then you still measure the same velocity. However, if you apply this equation, then you have a vector divided by a scalar. And in the scalar you have reflection and transmission. And in the Stokes you have only one the vector. And that means you cannot use this energy relation. And I think this is the same reason for the master equation.
I also want to stress that the Maxwell equation are very well-known limitation. For instance, if you have an electric arc in air or in empty space, you can still do some work with Maxwell equation. But if you have an arc within, submerged within a liquid, there's no calculation I can do. I cannot even define the resistance with the Maxwell equation. So there's nothing I can do. There is the ampere force. The electrodes attract each other. It's a longitudinal force. Brutal violation of Maxwell equation, etc., etc. So, as per everything in physics, there are very precise limitations. I'm sorry, I didn't.
No, time is limited. Let me ask the second technical question. In general, when your signal passes through barrier, it changes its shape.
Yeah, I have
yes. Therefore, how do you compare the signals on the time scale in order to measure propagation velocity? Do you make a maximum of signal, or do you refer to the front and so on? You need to compare two signals in order to determine the velocities.
We did both. With a network analyzer, you have a dynamic range of up to 90 decibel, 9 orders of magnitude, and then you see you don't have to amplify the two signals, the incoming and the transmitted. You understand what I mean? And then you can compare it, and then you see that it's really in front, the tunnel of the...
Let us continue this discussion in private way.
Usually this what I have shown you, this was amplified. This was amplified.
Make a short comment. If you write a free field theory, you of course have solutions with negative omega square, like free Klein-Gordon field, free Maxwell, whatever. That means that people used to think there are tachyons. But there cannot be any tachyons, because when there are tachyons, and there are interactions between the field, then the field will drop into a new minimum, and that will be stable. So like a house that has negative frequency square, it will collapse until it is a rack, and the rack will be stable. And that's with every field theory. That's why Landau showed that if you have negative omega square in helium, for example, you get a phase transition, and then you are stable. As long as you are in the unstable phase, of course you get it. And that's the answer to the question. There is never any tachyon. If the moment that these pseudo-tachyons have interactions among each other, then you have a new field, and the new field will settle at a new place, and that will be stable again. That's why, and you say also when you have your tunneling, if there's interactions, you ruin this possibility. You ruin immediately the tachyonic property. As long as you have no interaction between your particles, then you have tachyons. You cannot. But the moment they have interaction, it's gone, because you will have a phase transition. Okay?
Tachyons will violate causality in this case.
Yeah, but it's not just because the physics is unstable. That's the point. It violates causality because it's unstable. Okay?
That could be another interpretation, but there are no tachyons. Not tachyons, I think, in this.
Well,
he could not have transmitted a Beethoven symphony with tachyons.
That's the point, because it's unstable.
Is there any question, or we can proceed with... Okay. Thank you very much, Professor Nimtz.